Time for us to do some practice of Lagrange multipliers. Now, the idea of Lagrange multipliers are when we're solving a problem where we're optimizing subject to some constraint. So it's constrained optimization. Now, as with any optimization problem, often what's involved is a lot of being careful and a lot of computations, and in particular, where we get to have a systems of equations and we get to solve. So, algebra. We need to make sure we're getting our practice in, doing as much as we can, because the way we get good is through practice. We want to be good. In fact, we want to even be gooder than good. We want to be the goodest. Wait, that doesn't sound right. But anyways, the point is we want to become better. So if you're following along, make use of the pause button. See a problem you like? Pause it. Try it yourself first and see how you do. And if you ever need help, unpause. And then we'll try to figure it out together. Well, let's begin. Our first problem. Use the method of Lagrange multipliers. Hey, I think we're going to use the method of Lagrange multipliers. Yeah, totally gave it away here. Sometimes it's more subtle. To find the maximum of 2x minus y, given that 3x squared minus 4xy plus 2y squared equals 6, also find the point xy where the maximum is achieved. All right, now there's a little parenthetical comment here. The curve 3x squared minus 4xy plus 2y squared equals 6 is closed and bounded. In fact, it turns out it's an ellipse. It's an ellipse that's been turned sideways. And so the reason that it's closed and bounded, well, an ellipse, it's close. It doesn't have like a part of it shooting off to infinity. Now, why do we care? Well, we know if we have a nice function on a closed bounded set, it has to have an absolute max and an absolute min. So that's how we're guaranteed that we're going to have a max and a min. And you might start and say, okay. But we'll see some examples where it's like, where things can get a little bit interesting. So we have to be really careful as we look at our interpretation. Now, in essence, we need to identify two important functions. What are we optimizing, and what's our constraint? Now, oftentimes it's easy to figure out which is which. Here, we say, look, we're trying to find the maximum of 2x minus y. So that's what we're trying to do. We're trying to optimize our function f of xy equal 2x minus y. Our constraint, we look for phrases like given that, but we also look for equations where we say, some expression involving x and y equals a constant. That's a constraint. So our constraint is 3x squared minus 4xy plus 2y squared equals 6. So there's our constraint. So what we're trying to optimize and what we're trying to constrain. And we're going to think of this function here as g of xy. Now, how do we proceed? Well, what we need to do is figure out what are the potential points where a max and min could occur. And we'll figure out which one of them is a max and which one is a min. We could have several, not just two, but we should have at least two, right? Because if there's going to be a maximum, there will also be a minimum on our closed bounded set. So the key is to say, look, it has to be the case that gradient of f is parallel to the gradient of g. Or we can say gradient of f is lambda gradient of g. This lambda is where the idea of Lagrange multipliers comes in. All right, so what does that really say? Well, that really says, hey, we have a system of equations. F sub x is lambda g sub x, and f sub y is lambda g sub y. So let's write down what we have. All right, f sub x is 2. That has to equal lambda g sub x. Well, that would be 6x minus 4y. And then f sub y is minus 1. That has to equal lambda. And now we do our g sub y of minus 4x plus 4y. All right, so we get here our nice system of equations. Now there's a third equation, of course, this equation right here. So there's 1, 2, 3 equations. And there's x, y, and lambda. But the good thing is we don't really care about lambda. Lambda's not important. It's the x, y which are important, which is why our rule of thumb says solve for lambda. And in general, it's better to solve for lambda sooner than later. So what does that mean? Well, here that says, look, lambda, that's 2 over 6x minus 4y. But it's also minus 1 over minus 4x plus 4y. And now, okay, so just divide, divide. Okay, clear denominators by doing cross multiplication. So this becomes minus 8x plus 8y equals minus 6x plus 4y. So cross multiply, cross multiply. All right, now we're almost there. Just move some terms around. And that tells us negative 2x is equal to minus 4y, or a better way to say that, x should equal 2 times y. Okay, so we get x equals 2 times y. Fantastic. What do we do with that? Well, what we do is we say, look, this is a relationship between x and y. But we had another relationship between x and y from the original constraint. So now I have 2 equations and 2 unknowns. See, that's what we've essentially done, is we went from 3 equations with 3 unknowns, one of those unknowns being lambda. We knocked lambda out, so now we're down to 2 equations and 2 unknowns. Progress, progress. Actually, fantastic progress. Because what happens now? Well, I can come and I can replace here, everywhere I see an x, I'll put a 2y. So we'll have what? 3 times 2y squared minus 4 times 2y times y plus 2y squared equals 6. So I'm doing a substitution. All right, well, let's see. That'd be 12y squared minus 8y squared plus 2y squared equals 6. All right, well, that's something, right? Because if you take 12 minus 8 is 4, add 2, you get 6. So 6y squared equals 6. Okay, that says y squared equals 1, and that's fantastic. That tells us that y is 1 or negative 1, which means we have 2 possibilities. Now, we say, what happens if y equals 1? Well, x is 2 times y. So, in that case, this would lead us to the point 2, 1. If y were negative 1, x is 2 times y. So this would lead us to the point of minus 2, minus 1. And now we can say, aha, according to the method of Lagrange multipliers, there's 2 candidate points, 2 places where an optimum can occur. So we've now said we know where to look. We've narrowed down. We don't need to look at the whole curve. We say there and there. That's it. Those are the places to look. That's where your optimums are going to be. But we have to figure out which one is a maximum. So the last thing to do is plug into our function. All right, so let's do a little bit of plugging into our function. If we plug 2, 1 in, what do we get? Well, we're going to get 2 times 2 minus 1. That's 4 minus 1, also known as 3. If we plug in minus 2 minus 1, well, we're going to get minus 4 minus minus 1. Well, that's negative 3. And now we say, okay, one of these has to be the max. We find which one is the largest one. And we say, aha, 3. 3 is bigger than negative 3. True story, true story. So our conclusion is the max equals 3, and it's achieved at the point 2, 1. And we're done. Good. So this is the typical process that you see for Lagrange multipliers. All right. Figure out your optimization, figure out your constraint, set up your gradient of f equals lambda gradient of g. When in doubt, solve for lambda. And I find myself full of doubt, so I almost always do that. And get to another equation, in other words, another relationship between our variables. Okay, now that solves for points, and then comes the interpretation. And that can be a fun process, the interpretation. Well, good. Now that we've had a nice warm-up problem, let's keep it going. And let's try another problem. Okay, so for xy greater than or equal to 0, all right, that just really is a way of saying, hey, we're in the first quadrant. Find the optimum of 3xy minus 5y, given that 4x plus 3y plus xy is 30, and is the optimum a min or max? It's a little bit poorly phrased, this problem, and I blame the problem writer. That's me, I wrote it. But okay, let's think about what it's trying to say. It's saying, hey, there is this function we're trying to optimize. All right, so we know it. And this curve here, by the way, this is the curve 4x plus 3y plus xy equals 30. It's this one right along here. Let me mark it a little bit better so you can see what's going on. So our question becomes, okay, you have this curve, and we're looking for an optimum value of the function along this curve. Now, because we care about the endpoints, we should take a second, just really briefly, and talk about what happens. So for instance, here, when I have x is 7.5 and y is 0, well, if y is 0, we see, oh, that says you're going to have an output of 0 for your function. If we're over here, so this is at x equals 0, but y equals 10. So we're going to get 0 minus 5 times 10. All right, so over here, it's negative 50. So we're 0 there, we're negative 50 there, and something interesting probably should be happening in between. That's what it's after when we're talking about the optimum. What's happening in between, and what is it? Is it a max, a min, something else? Well, we'll figure it out. We'll figure it out. So we start our process. Well, what are things we're optimizing? What's our constraint? The thing we're optimizing, well, that's pretty easy. It tells us optimize this function, 3xy minus 5y. We can kind of also tell it's what we're trying to optimize because it's not our constraint. Our constraint is pretty easy to identify most of the time. It's some function equal to a constant. So our constraint is what? Well, this 4x plus 3y plus xy equals 30. And again, we're going to think of this left-hand side as g of xy. Now, if both sides had variables, that's easy to do. We would just move everything over to one side, right? We say, hey, let's take some of the variables on one side, move it to the other side, so that all our variables are on one side for our constraint, because we really want to have our function equals number. That's the kind of constraint we want. Function equals number. All right, so we begin. The process says we want to look at gradient of f equals lambda gradient of g. So let's start there. Now, this really is just a condensed way of saying, hey, we have a system of two equations and two unknowns. So fx equals lambda gx, and fy equals lambda gy. So f sub x, 3y. That has to equal lambda g sub x, 4 plus y. Okay, great. F sub y, 3x minus 5. Wonderful. That is equal lambda g sub y. Well, 3 plus x. And now we say, look, three equations, 1, 2, 3. But we can knock out one of the variables and reduce it down by remembering, when in doubt, solve for lambda. You might hear me say that quite a bit when we go through these problems. Well, because it's a good way to approach problems. So that's why we're sharing our knowledge. That's what we want. We want to drop some mad knowledge on ourselves. Okay, so solve for lambda. In the first equation, you get 3y over 4 plus y. And in the second equation, 3x minus 5 over 3 plus x. Now, you might at some point object and say, Steve, I'm not comfortable with this idea of solve for lambda because I worry about dividing by 0. Okay, I get your concerns, and that is a valid concern. But if you go to the next step, which is cross multiply, then you no longer have to worry. So if you solve for lambda, set up your relationship and cross multiply, then you get to a true relationship. There's no division by 0. That you can justify everything without doing any division by 0. Life is fine. So don't worry too much about problems. Worry about solutions, right? That's what we want. Okay, so this leads us to 3 times y times 3 plus x equals 3x minus 5 times 4 plus y. Oh my goodness, there's a lot here. Well, start expanding. 9y plus 3 times xy equals 12x plus 3xy minus 20 minus 5y. Now, if the problem has been well set up and we've been living a good, clean algebra life, something good should happen right around here. And in our case, we're like, ooh, something good is happening. The 3xy's are canceling. Nice. And, well, we can keep it going, right? If we add 5y, that says, look, 14y is equal to 12x minus 20. Okay, so we can either solve for y or solve for x. It doesn't really matter which one. I mean, we have to just solve for one of them, right? So, well, which one to solve for? Good question. Well, let's not worry too much about that right now. Let's solve for y. Let's do it. It shouldn't be too bad. So what do we have? If we first notice, divide everything by 2 because they all are even, then we'd have 6x minus 10 over 7. All right, so now we have a nice relationship for y. And, all right, so what does that say? Well, it says that if we're at the optimum, where the gradients are parallel, we need to have 6x minus 10 over 7 equals y. You can almost visualize what this says, because it says, hey, y equals 6x minus 10 over 7, it's another curve. It's a line. It has an intercept of negative 10 over 7 and a slope of 6 over 7. So it's doing something like this. And so now, in essence, if we want to satisfy both the constraints, it's like we're trying to find the intersection. So it's like, okay, we're suspicious. It looks like there's an intersection point. That's good. Got to find it still. Well, that's all right. Now with our relationship, we can substitute in. Okay, so into the constraint we go. And what do we get? Well, let's see. We'll have 4x plus 3 times 6x minus 10 over 7 plus x times 6x minus 10 over 7 equals 30. All right. Well, there's fractions here. Let's just get rid of our fractions really easily, super clean. Just multiply everything by 7. And if you do that, we'll have 28x, 4 times 7. And here, the 7's cancel. So we'll have 18x minus 30. Here we'll have the 7's cancel, so it's 6x squared minus 10x. And here we'll get 210. All right. Well, let's keep going. What can we do next? Well, we can group terms, right? So I feel like I didn't plan well. 6x squared. Then what do we have? 28 and 18. That makes 46. Subtract 10 makes 36. So plus 36x. Then we have minus 30. And we'll bring the 210 across. So minus 240 equals 0. Okay. Well, we're running out of space. That's why I said I didn't plan very well. If we divide everything by 6, that turns it into a relatively nice polynomial. X squared plus 6x minus 40 equals 0. Okay, so quadratic. Nice. We love quadratics. So what are we looking for? We're looking for two numbers that multiply together to give negative 40, so they'll have opposite sign, but add together to give 6. Well, 40 is 4 times 10, right? And if you 10 and negative 4, that 10 times negative 4 is negative 40, and 10 plus negative 4 is 6. Okay, so that would say what? Well, we should have x minus 6, x minus 4, x minus 4, x plus 10. So let's check, right? X squared, that's good. Plus 10x minus 4x, that's 6x, and minus 40. Good. And so we say, look, there's two possibilities. There's x equals 4 or x equals minus 10. But wait a second. At the very beginning, it said, look, x is positive, greater than or equal to 0. That one's gone. So we know the x coordinate is 4. All right, what's the y coordinate? Well, now we plug it back in. So y would be 6 times 4, which is 24, minus 10 over 7. Okay, 24 minus 10 is 14. Divide that by 7 gets us to 2. So we have, our point is at x equals 4, y equals 2. Okay, so there we go, 4, 2. So that's where an optimum is likely to occur. Let's figure out what's going on here. So that's a location. Now what we want to do is plug that in. Okay, so if we think of the function at 4, 2, so that's what? 3 times 4 times 2. Okay, that's 24. And then minus 5 times 2, that's 10. 24 minus 10 is 14. Okay, so we say, great. At this point, at 4, 2, it's 14. So now we're ready to think about what kind of point is it. Is it a min or is it a max? Or is it neither? And for that, we say, well, what's happening? Well, we can read it off. It's starting at 0, going to 14, and going to negative 50. And it can't be changing behavior at any other point, because if it ever changed behavior, that would have been an optimum that would have been picked up by the process. So you see, we're going up to 14 from both directions. And so we can say, an optimum value of 14, which is a max. And there we go. We found where it happened, what the value of the function is, and what kind of point it is, namely that it's a maximum. Cool. Wow. Nice. Good warm-ups. All right. Well, time to keep going. So, our next problem. A word problem. Maybe an essay problem by its length. You are part of an expedition to Mars. An emergency evacuation caused by a severe storm resulted in you being mistakenly left behind and presumed dead. I hate when that happens. All right. You realize that'll be years before anyone will be able to come help you. And you know that the only way you will be able to survive is if you calculus the heck out of your situation. A first priority for you is to work on growing food. As the team's botanist, you have brought some tomato seeds for experimenting, and you find some potatoes that have been sent as part of a Thanksgiving meal. Oh, so we have two options, tomatoes and potatoes. That's nice. You have also been able to create a makeshift patch of soil that you can use for growing crops. Good news. You know that you have extremely limited resources, and so you want to make sure you use as little water as possible and still be able to grow 14 plants. So this gets to the whole point of optimization. Limited resources, making the most of everything. And there's something I noticed in that sentence. That's a number. Of course, they wrote it as a word so that we maybe wouldn't catch it, but that's a number. And when I'm doing a math problem, I'm like, ooh, number. Ooh, okay, so I suspect that's going to be important. So why 14? Well, that's the number you need to sustain you nutritionally. In particular, you note that if you plant pea potato and T tomato plants, then the amount of water used will be 3t squared minus 3tp plus p squared. Kind of like that minus 3tp says there's some benefits to growing both simultaneously. So that you know, if you grow them combined, well, it takes a little bit less water than if you were to go wholeheartedly into one kind. Use the method of Lagrange multipliers to find the optimum number of potato and tomato plants that should be grown to minimize water usage. What a problem. What a great problem. Okay, well, let's think about this. Now, maybe the first thing to think about is, do we really need Lagrange multipliers? Let's talk about what the problem says. Oftentimes, if it's a very long problem, it probably has a pretty short answer. So let's identify our various things. So we know what we're trying to optimize. We want to make sure we use as little water as possible. Why? Because that's what it tells us. Make sure to use as little water as possible. We also know the formula for how much water we have. It's this formula here. So we want to optimize our expression 3t squared minus 3tp plus p squared. So we'll call this a function of p and t. Notice it doesn't matter that it's not x and y. There's nothing special about x and y. We are adaptable. We can adapt to any variable names that are needed. All right, now what's our constraint? Well, the constraint is we need to grow 14 plants. And so we want to say, look, we have to grow 14. We don't want to grow 15. That would require us to use more. And so we want to grow exactly 14. So our constraint, it's not written down as an equation, and that's the fun. We get to figure it out. So our constraint says, hey, p plus t equals 14. Now, if you were to put on your Calc 1 hat, what would you do at this point? You would say, well, let's just do the following. Solve for one of our variables, say p equals 14 minus t, plug it in and get our optimization down to a single variable and go from there. And you'd get the right answer. You know, I'm not going to lie to you. It's going to work this time. But there will come problems where you can't do that, which is why we're saying, look, use the method of Lagrange multipliers, even though, yes, we understand that in many simple problems, there are other ways to do it. We know that there are other problems where you couldn't do it. And so we want to make sure that you can handle those as well. All right, so we begin. Remember our constraint. Here's our function. We'll call it g of pt. So what happens? Well, we need to have our parallel gradient vectors. So f sub p is lambda g sub p, and f sub t is lambda g sub t. All right, well, take the derivative with respect to p. Minus 3t plus 2p is lambda times 1. Well, that's easy. And take the derivative with respect to t. 6t minus 3p is equal to lambda times 1. Wow, well, that's great. It's really easy to solve for lambda. We're done. So what's the point? Well, the point says, look, they both equal lambda, so they also have to equal each other. So in other words, minus 3t plus 2p has to equal 6t minus 3p. All right, well, we can add 3p, we can add 3t, and that tells us what? Well, 5 times the number of potato plants has to equal 9 times the number of tomato plants. All right, well, great. Now that's a relationship. And so now we come up to this relationship, say, well, we've got to figure it out. Okay, well, we're going to substitute. Well, let's start. If I know p plus t equals 14, let's say I multiply by 5, because I want to put in a 5p. So 5p plus 5t equals 70. But wait a second. 5p is 9t. So 9t plus 5t is 70. Or 14 times t equals 70. Or, that says our number of tomato plants, 70 divided by 14, is 5. Great. Well, if t equals 5, 9 times 5 is 45 divided by 5. That says, hey, the number of potato plants is 9. Okay, and we're done. We're actually done. Well, one thing we might do is we might say, look, 5 tomato and 9 potato. And that's about it. Well, that's what we're done. So you see, sometimes the problems with the longest statement are very, very quick. Now, you might stop and say, this is a little unrealistic because we ended up with such a nice answer. I mean, often if we do these problems, are we going to end up with terrible answers? Yeah, and oftentimes in real-world situations, or maybe real off-world situations in this case, you might end up with a strange answer. But the point here is we have a process to find an answer. If we had gotten our answer was, oh, you should grow 5.6 tomato plants or something. Well, we say, look, we can't grow a fraction of a tomato plant. Then we'd say, okay, just round to the nearest plant. And so we know that in real-world situations, we do have to adapt. But, of course, the fun problems that we can solve now, we can still solve them. So that's good. Well, let's keep going. And on to our next problem. Use the technique of Lagrange multipliers to find the maximum value of the function xy plus y, given that 9x squared plus 10y to the fourth equals 9. I will tell you that there is definitely a maximum here, in that if you look at this curve, it says, look, both these terms are greater than or equal to 0. And so x can't be any bigger than 1, because otherwise this is already at least 9. Forget it. And y it definitely can't be 1. It has to be smaller than 1, because otherwise, look, forget it. It's already at least 10. So it means you're nice, closed, and bounded. Great. So we know we have a max. Whew. Actually finding it, well, that'll be fun. So we kind of see it, right? We know what we're trying to optimize, and we see this is our constraint. Perfect. Well, let's jump right in. So we start by saying, what is our system of equations that we need to set up? Well, we're going to have f sub x is equal to lambda g sub x, and f sub y is lambda g sub y. All right, well, this becomes f sub x is y, right? Take the derivative with respect to x. You get y equals lambda g sub x, well, 18x. And on the other hand, f sub y, that's x plus 1 equals lambda, and g sub y would be 40 y cubed. Well, not looking too good right now. I'm have my doubts. And when in doubt, solve for lambda. All right. So lambda would be y divided by 18x. That's if we use the first equation. Or we could say, hey, it's also x plus 1 divided by 40y cubed. And that's if we use the second equation. Multiplying across, we'll get 40 y to the fourth is equal to 18x times x plus 1. All right. Well, as they say, what can we do? Well, we look at it and we say, this is one equation, and remember, we have this other equation. 9x squared plus 10y to the fourth equals 9. So what we want to do is look for ways that we can combine things together. And I can't help but notice they both have a y to the fourth, and that's their only thing that has a y involved. So it's like, perfect. Let's use that. So what can we do? Well, there's lots of things we can do. We can think of substitution, for instance. We can also do something like this. We can take this equation, say multiply, for example, by -4, and combine. You get minus 36x squared, 40y to the fourth minus 40y to the fourth, gone, equals, over here, 18x times x plus 1, which we can multiply that out. That's 18x squared plus 18x, and minus 36. Well, that's now a quadratic in x. We have hopes to solve that. Okay, so we keep working on that. If we move the 36x squared across, 0 equals 54x squared plus 18x minus 36. Great. Now, what would be good? Well, we want to solve it. It'd be really good if it factored. Almost too good, right? Almost too good to hope for. But we should have hope. We're in calculus. We always have hope that there's going to be a beautiful answer. So let's see. 18 does go into 36, and it also goes into 54. They're all multiples of 18. All right, so 18, then that would be 3x squared plus x minus 2. And now we look at this and say, can it factor? Whew, oh, this is going to be interesting. Okay, we have to think about this because it's not x squared, right? It's 3x squared. But it kind of says if it does factor, there's not a lot of ways to write 3. So the only thing that would happen is a 3x and an x. Now for 2, a lot of ways to write 2, 1 and 2. If we put a 2 there, so put 2 in that slot, that'd be a 6x and an x. No way to get down to x. So the only chance is if we put a 2 there and a 1 there. Last thing to do is think about the signs. Well, if we made this a minus and this a plus, it'd be minus 3x plus 2x. No, that's not going to work. Okay, if we make this a plus and that a minus, 3x minus 2x. Okay, I think that's right. Okay, so let's check this. I'm going to put this in. Okay, check, right? 3x squared, good. 3x minus 2x, x, good, minus 2. Okay, good. Which tells us what? Well, it tells us that, look, we have two possibilities. X is -1 or x is 2/3. Okay, so let's start with the -1. If x equals -1, where does that take us? Well, let's follow it through. So x equals -1. That would say, I can use any relationship. For instance, I can use this relationship. I would say 9 plus 10 y to the fourth equals 9. Well, that would tell us y to the fourth has to equal 0. There's only one way that can happen. That says y equals 0, and that means we're at the point -1, 0. Okay, so this is a point we have to look at. Not the only one, but it's one we have to look at. 2/3 now. If x equals 2/3, what happens? Well, plug it in somewhere. Well, okay, look, we can plug it in anywhere. I can plug it in there. So 9 times 2/3 squared. That's 4 plus 10 y to the 4th equals 9. Well, look, subtract 4, divide by 10, and what do you see? Well, that really says, hey, y to the 4th has to be a half. You know, because like 10 times a half is 5 plus 4 equals 9. Okay, which means y is equal to the 4th root of 1/2. Okay, wow, what a number. Well, I mean, it has to be something, so there it is, the 4th root of 1/2. Okay, good. So, plus or minus, right? Because it's the 4th power, so it could be either sign, which leads us to 2 points. 2/3, comma, positive 4th root of 1/2, and 2/3, comma, negative 4th root of 1/2. All right, well, we have 3 points to check. And last thing to do is plug each one into our function. Before we do that, let's try to make ourselves a little bit happier. In other words, try to make it easier to evaluate. Because remember, we love ourselves. We want to make sure we take good care of ourselves. We're going to be with ourselves for a very long time. So we want to look back at this time of calculus as one of like joy and like, I'm so glad I got to do this. Notice our function. One way to think of our function, xy plus y, is we can also think of it as factoring out the y, so y times x plus 1. So what happens? When we plug in minus 1 comma 0, minus 1 plus 1 is 0, and then times 0 says, okay, that produces 0. All right. Now, what happens if we plug in here? Well, 1 plus 2/3 is 5/3 times the value of y. So we get 5/3 times the 4th root of 1/2. So that's the value we get there. Here, well, x plus 1 is still 5/3, but now times negative. So this would produce a value negative 5/3 times the 4th root of 1/2. So we found that there were 3 interesting points. The maximum has to occur at one of them. We plugged it in and we got 3 numbers, a 0, a positive, and a negative. If we're after the max, well, it's the positive one. The positive one is going to be larger than 0, and it's going to be larger than the negative. And so we come to the conclusion that our answer is 5/3 times the 4th root of 1/2. And that's it. We're done. Wow, what a number. What a number. I certainly don't think we would randomly guess that as the answer. Well, thank goodness we don't have to guess. We have tools. Our tools will help us find the answers. Great. Well, let's do more problems. Always more problems. Okay, our next problem. You have been hired to paint 3 large, non-overlapping circles, red, blue, and green, on the side of a building. Now, the sizes of these circles was left to you. Oh, we get to choose. Okay, so we should draw ourselves a picture, and of course, it doesn't have to be a great picture. So we have this building here. Okay, so here's our building, and what's happened? Well, we're going to paint 3 circles: a red one, a blue one, and a green one. Okay, so we have a red circle, and a blue circle, and a green circle. Now notice the sizes are up to us. So maybe we'll have different sizes. So who knows? Let's see. There's more to be said, right? Well, we can say the following. The sizes of these circles was left to us. However, the total area had to be 200 pi square meters. Okay, so, all right. And what else? The contract gives you 3x gold bars. I like this contract. Being paid in gold bars? Nice. All right. Well, hold on. Let's keep going back here. 3x gold bars for the painting the red circle of radius x. Okay, so the red circle has radius x. Just make a note here. 4y gold bars for the blue circle. Okay, so that's radius y. All right. And 5z gold bars for the green circle. Nice. And the question is, what radii should you choose for the various circles to maximize your gold bars? Now, sort of our naive answer would be, hey, I make a lot of gold bars for that green circle. So I should forget the red and the blue, just paint as big of a green circle as I possibly can. And maybe that's the answer. It's possible. It's possible. And maybe it's not. That's also possible. And let's see what the math says. On a side note, let's just, for comparison later on, if we did put all of our paint into the green circle, well, what would that say? Now, we can work it out. That would say, look, if it was all in the green circle, the area, well, that would be pi z squared, and that would be 200 pi, which tells us that what? Z would be the square root of 200, which is 10 times root 2, which is 14 point something. So if you paint only a big green circle on the side of the building, you'll get 14 gold bars and a little bit. But can we do better? And if so, how? Okay, now one of the things that makes this interesting is there's no equations given to us. We suspect this is going to be a Lagrange multiplier problem because, well, look at us. We're doing Lagrange multiplier problems. So what are some things that are hinting in this problem that we should be thinking Lagrange multipliers? Well, there's a couple of things, right? We have some constraint. Well, where is that? The constraint is in the total area must be 200 pi. Okay, that's a constraint. When we have something must equal, okay, that says you have some expression equals something. Constraint. So we know there's a constraint. We know that there's an optimization because it says, look, we want to maximize something. When we see a word like maximize, that tells us, hey, we want to optimize. So we know that there's a constraint when we're trying to optimize, and constrained optimization is Lagrange multipliers. Okay, so we need to figure out our equations. Our two equations are, what are we trying to optimize? What's our constraint? Well, we're trying to optimize our gold bars. So we're going to think of our function. We have three things we get to choose. So we're taking it up a notch, right? 3 variables instead of 2. But the processes are the same. So we'd have what? Well, 3x gold bars, 4y gold bars, and 5z gold bars. All right, so there's what we're trying to optimize. Our constraint, well, we take the areas. So our areas would be pi x squared, pi y squared, and pi z squared. Pi z squared, and that has to add up to 200 pi. Well, there's a lot of pi's going on here, so let's cancel some pi's. So we could write our constraint as x squared plus y squared plus z squared as 200. All right, and we're going to think of this side. That's our function g of x, y, z. All right, so we're ready to begin. Here we go. our basic formula says gradient of f is lambda gradient of g. And that's true for any number of variables, 2 variables as well as 3. So we say, look, that gets us to 3 equations. Fx equals lambda gx. Fy equals lambda gy. Fz equals lambda gz. Okay, well, let's do that. Fx gives us 3 equals lambda. Gx is 2x. Fy is 4 equals lambda. Gy, 2y. Fz is 5 equals lambda. Gz is 2z. All right, nice and 2z, right? Well, maybe not 2z, right? But okay. Solve for lambda. Actually, we can solve for 2 lambda, right? Because they all have 2 lambda. We can say, hey, lo and behold, this says the following. 2 lambda is equal to 3 over x, and it's also equal to 4 over y, and it's also equal to 5 over z. Well, just flip everything. X over 3 is the same as y over 4, is the same as z over 5. All these things are equal to each other. Now, we can use this to reduce to one variable. In other words, I can rewrite x, y, and z in terms of a single one. Now, it doesn't matter which one we pick. Let's pick x. So we can say, all right, well, that if we solve for y, that says y is 4/3 times x. Solve for z, z is 5/3 times x. Now you might say, well, what is x? That's the easy one. Turns out that x is x. Good to know. So using our constraint, gradient of f equals lambda gradient of g, we can really get relationships between our variables and simplify our equation. Get some new relationships. Let's take our relationships and plug it in for x, y, z. All right, so we now have the following. X squared plus y squared becomes 4/3 x squared plus z squared. Well, that's going to become 5/3 x squared equals 200. Well, that's x squared plus 16 over 9 x squared plus 25 over 9 x squared. All right. Well, of course, we should point out that x squared is also 9 over 9x squared. True. So, what do we get? Well, if we add, because they all have a denominator of 9, 9 and 16 and 25, they add up to what? Add up to 50. So, we get 50 over 9x squared is equal to 200. Well, great. See, 50 goes into 200. 200 divided by 50 is 4 times 9 says, hey, cool, good news. Choose x squared, to be what? Okay. I got ahead of myself. So you'd have 200 divided by 50 is 4 times 9 is 36. And now we're basically home free. Well, what can x be? 6. And then you're like, oh, what about negative 6? Well, I can't paint a circle with negative radius. It's not like, well, I'm going to come into the building and like chisel something out of the wall. I mean, doesn't make any sense. So there's sort of the, constraint of the natural problem. So it says perfect. That says x should be 6. So, okay, so 6, 4/3 times 6, well, that'd be 4/3 times 6 is 4 times 2, which makes it 8. 5/3 times 6 would be what? Would be 10. All right, great, good. So, what does that lead us to? Well, that leads us to saying we think the answer is the following. And we want to compare it to the other possibility. But according to our process that we ran through, it says, okay, so x is the red circle. So the red should be 6 meters for the radius. Y is the blue circle. The blue should be 8 meters for the radius. And Z is the green circle, and that should have 10 meters. And on a side note, how much do we get? How many gold bars? We put a lot of work in. What's our return? Well, 3 times 6 is 18. 4 times 8 is 32. That's 50. And 5 times 10 is another 50, which gets us a grand total of 100 gold bars. Now, how does this compare? Because remember, we also said that one of the things we could have done is just make one big green circle. That's our naive approach. Now, if you made one big green circle, the radius would be 14 and change. So maybe let's just round it up and say, okay, 15. And if we got 5 gold bars, well, that's 5 times 15 is 75. That's a lot less. We'd have lost quite a number of gold bars if we just did our naive, pour it into the thing which makes the most profit. Now, why did this turn out this way? Here's sort of the intuition. It says, look, when you have the radius, it doesn't take a lot of area to increase the radius if the radius is small, but as your radius gets big, a small change in radius can significantly increase the area. So sure, initially it makes sense to say, okay, we really want to put a lot of money into the green, but after a while, it takes us so much area to expand the radius a little bit, it says, look, it's no longer worth it. We should be putting it into these other circles where with a small amount of area, we can get a pretty good chunk of radius. So there's kind of a nice balanced trade-off between these different circles. And that's what optimization really deals with in the end of the day. It's like, what's the right trade-off? What makes things work? And that's what we want to do. We want things to work. It's much better than not working. And gold bars. Wow. Someday maybe I'll have a job where I get paid in gold bars. Not yet. Well, if you're going to become a mathematician, you got to take a vow of poverty. So probably never will. I think we have time for one more. One more problem. Okay, and this is sort of, before we start, I'm going to tell you, this is a word of warning. This is not going to go how you expect. Okay, so here we go. Maximize 1 over x plus 1 over y subject to x plus 4y equals 1. And the wording on this problem is taken directly from an old exam. In fact, it's from an old final exam. And it was from a really curious final. And I can't go into the full story now, but let's just say things happen. Things happen. And one of them is this. So we look at this and say, okay, I'm optimizing because I see the word maximize. There's a subject to, which means there's a constraint. Lagrange multipliers. All right, perfect. I'm happy with that. And let's just go ahead and work through the process. So we have our function, f of xy is 1 over x plus 1 over y. Our constraint, x plus 4y equals 1. So this is our g of x comma y. All right, so far, no big surprises, right? No, nothing will surprise us until we get to the end. So don't try to overthink the beginning. Okay, so we do our gradient of f equals lambda gradient of g. And if we do that, well, what do we get? Well, we have f sub x equals lambda gx, and f sub y is lambda gy. All right, well, derivative with respect to x is negative 1 over x equals lambda, and here, derivative of g sub x is 1. Well, that's great. Whoops, not negative 1 over x, negative 1 over x squared. There we go. F sub y, derivative of 1 over y, is negative 1 over y squared equals lambda, and g sub y is 4. All right, well, it's not so hard to see. If you multiply the first equation by 4, you both get 4 lambda. So minus 4 over x squared is equal to minus 1 over y squared, and they both equal 4 lambda. All right. Now, on a side note, we have to rule out x equals 0 and y equals 0 because it's not part of the function. Let's not worry about that. That is part of our story at the end, but for now, we proceed. We can get rid of the negatives and we can cross multiply. So we come and say, hey, 4y squared should equal x squared. All right, well, what does that say? Well, it says there's two possibilities. When we take the square root of both sides, well, it could be that they had the same sign, so x equals 2y, or it could be they have different signs, so x equals negative 2y. Now, technically, what would have happened if you took the square root is you get 2 absolute value of y equals absolute value of x. But then you say, okay, they both have the same sign or they both have different sign, and so you get to these two equations. Well, now we say, okay, let's see what we have. Suppose x equals 2y. Well, if we follow this through, so I can replace 2y by, I can replace x by 2y. So 2y plus 4y equals 1. All right, or 6y equals 1, or y equals 1, 6. Now, if y equals 6, x is twice as big, so that gets us to the point 1/3, comma, 1/6, yes? Yeah. All right, great. Now, if x equals minus 2y, okay, well, what happens? We get minus 2y plus 4y equals 1, or 2y equals 1, or y equals a half. Okay, plug that in. Well, x is minus 2 times a half makes that minus 1. All right, fantastic. Now, the fun part. See, look, we got 2 points, right? And so these are the places where optimums can occur. Well, what happens when we plug them in? So we say, aha, f of 1/3, comma 1/6. Well, look, you just flip them over, right? 1/3 becomes 3, and the 1/6 becomes 6. And so this is really going to become 3 plus 6, which is 9. All right. And f of minus 1/2, well, again, you flip things over. Minus 1 becomes minus 1, half becomes 2, and you get minus 1 plus 2, which is 1. Now, let's go to what the problem was asking. It said maximize this, subject to our constraint. Which one of these two is the max? I know what you want to say. Go ahead. You can say it. Go ahead. I know it. The 9, right? The 9 is the max. Isn't it? Yes. Okay. All right. So this is the max and this is the min. Right? 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 No. It turns out. Now, by the way, nobody caught this. None of the instructors, none of the students caught what we're about to talk about. And this was just like after the exam, someone said, wait a second, there's something fishy here. Okay, it turns out that 9 is actually not a max, it's actually a min. And 1 is not a min, it's actually a max. And at this point, you're going to really lose faith in me as an instructor. Steve, how can it be that the max is below the min? You've been doing problems for too long, Steve. You need to take a break. Let's actually talk about what happened here. There's something curious going on. And when we say they're a min and max, we should say it's a locally. In other words, if you look at what's behaving nearby. So let's think about our situation. We have our plane, and we look at x plus 4y equals 1. X plus 4y equals 1, well, that would be a line, which says, well, look, we want to maximize our function over this line. It happens to here at 1, happens to over here at 1/4. Well, except, of course, we can't talk about what happens if we pass through one of these points here. So at these points, they're sort of verboten, off limits. Now, we got 2 points that showed up. One point was here at 1/3, negative 1/6, and the other point was over here. And at this point, what we want to do is to be a little bit careful and think about what's happening. So, we know the value of the function at this point is 9. What happens to our function as we move closer to the axes? Well, what happens is if I'm close to the axis here, 1 over x will be a very large positive number. And 1 over y is like 4. So it's actually going off to infinity on these sides. So similar if you go down towards here. So it's coming from infinity down to 9, back up to infinity. So 9 is a min. It bottoms out. So that's what we mean by 9 is a min. Well, what happens on this side? If I'm on over here, 1 over x, well, it's 1 over a very tiny number, makes it a large negative number. So that's the negative infinity. And now, what happens as we come to here, we get to what? Well, we get to the value of 1. And then imagine we went a long, long, long ways away. Well, if we head off way, way far in the distance, x will be large, y will be large. So 1 over x will be small and 1 over y will be small. So it's going to go to 0 as we head off that direction. So I'm going to go from negative infinity to 1 back to 0. And so that's why that's a max locally. So what is the correct answer? Well, we could say that in terms of the constraint optimization, that the points which are interesting on the curves are these points, 1/3, 1/6, negative 1.5, and they're where a min and a max occur locally. But the actual answer, if we take it literally as asked, how big can this function be? 1 over x plus 1 over y? Well, the answer is it can be arbitrarily large, because as I get close to one of the axes, I'm going to blow up. So technically speaking, the answer is infinity. And this shows you the danger. Be careful. Be careful. Don't just naively take the answer out and say, okay, great, that's it. Think about what's happening. Think about what's happening to your function at other points. And that's why when we run the process of Lagrange multipliers, it tells us where interesting things are, but it doesn't tell us what the interesting thing is. And for that, we kind of have to say, what's the behavior on either side? You got to probe a little bit, and you have to have context. When it's closed and bounded, we don't need context. We say, look, closed and bounded, we're definitely going to have an absolute max and absolute min. Life is fine. But otherwise, be careful. This goes, by the way, for test writers. If you're writing a problem about Lagrange multipliers, don't just be like, oh, it'll work out. Well, sometimes it doesn't. And I'd like to say this is the only time that this has ever happened. But it's not. We'll get to that probably in a different practice session. But for now, I think we've had a good session. Thanks for coming, and I hope you have a great day. Bye.